Okay, welcome everybody. I'm going to do our second take of the tutorial for today. So we're talking about milestone 4 in parallel programming, and we'll also talk about this in the lecture on Wednesday. So the ideal would be you saw that lecture before this tutorial, but it'll be okay this way too. Okay, so in milestone 4, you're solving this traveling courier problem. And as you know, you've got depots, pickups, drop-offs, trying to find the fastest delivery route. And part of getting a good delivery route is estimating the travel time between all these locations. And you can use that to help you find a good delivery ordering and then eventually connect everything together in a path. Okay, and you have to do this in less than 50 seconds. So, as we talked about in lecture, to get better estimates of travel times, you can pre-compute all the interesting paths. So paths between your pickup and drop off and depot intersections and put them in a matrix or something like a matrix. So I'm showing here the rows are the from intersections. So intersection 1 to intersection K. Actually, I should label these in the wrong order in a way, but intersection 1 to intersection K. And every entry in the matrix gives me a travel time from some intersection to some other intersection. And I can use that to basically do a better estimate of what is the travel time for a given order of deliveries. I could have used distance, that's fast, it's easy, but it's not as accurate. Okay, so I want to use exact paths instead because I'm ambitious, want to do well in the leaderboard. It's more accurate, but it's slow. Okay, so how are we going to compute that travel time matrix? So just quickly review a few things we went over in lecture. We could do this with a double nested loop. Okay, so we've got k interesting intersections. That's our sum of our pickups, drop-offs, and depots in a graph with n total intersections. Okay, so this outer loop, we're going to go through k times. This inner loop, we're going to go through k times. And we're going to invoke our A star algorithm. So this is just if I took my best algorithm from milestone 3 and used it to find all these travel paths. And I'd have to use, because it only finds a path from one source to one destination, I have to invoke it a lot of times, right? I've got two loops here. Okay, so I didn't actually bother making the poll, but just type in the chat, what do you think the complexity of this is? And this isn't the best algorithm we went over in lecture. This is if you just took your M3 algorithms and directly used it, your A star algorithm. So what do you think the complexity of this is? These are some of the questions that you often get, by the way, in the final presentation. So good to think about. Yeah, so Truman says k squared n log n, and it's exactly right. So I've got a loop over k here, a loop over k here, so that's k squared. A star's complexity is actually the same as Dijkstra. It tends to be somewhat faster, but it's faster by a constant factor. An A star algorithm can still put every one of your intersections into the priority queue, and when you put it into the priority queue or take it out, it's log n work with a conventional priority queue. So k squared n log n is a good answer. And this actually is going to be a problem for the bigger test cases that we give you to run that in 50 seconds. Okay, so how can we speed this up? Well, algorithmically went through in lectures that we can get rid of one of those loops. We could just loop over all the starting points. So that's still k interesting intersections. And then we could basically invoke a variation on Dijkstra that from that source will find all the destinations, all the paths to all the interesting intersections, all k of them, all at once. So for that, what do you think the complexity of this is? Given the answer to the previous one, the answer to this one's not too hard. Yeah, so this one is just k, because that's how many times I invoke it. It's Dijkstra also can take every node in the graph, so n, put them into a priority queue or wavefront, which is log n, also takes them out of a priority queue or wavefront, which is also log n, so it's k n log n. So that is a big speed up, so k times faster. Okay, so big speed up, especially if k gets large, and k for some of the problems we give you can get to several hundred. So this is a really big speed up. You want to get this. Okay, why am I showing you this? Because we're talking about parallelism in this lecture, but we don't want you to think the first thing you do when something's not fast enough is make it parallel. The first thing you should do is try to improve your algorithm. And if we had used the naive algorithm here, our A star algorithm, we'd have something much, much slower. So first we want to get the algorithm good. But if this still isn't fast enough, or we just want more speed, then we have to go to parallelism, because now we've basically got a very good algorithm. Okay, so let's talk about parallel programming. So far in your career at U of T, you've been writing what are called single-threaded programs. When the program starts, it starts in the main routine, and the C runtime or C++ runtime creates one thread for you. So you've had one thread of execution without ever thinking about it. But in modern CPUs, you have more than one core. Okay, so a core is basically like a processor. It has its own program counter so that it can be running different instructions. But all of these cores, so each of them has their own registers, their own program counter, etc., can be doing different things, but they all share one memory. Okay? This is a pretty deep topic, so we're not going to go into exactly how these work, but if you want to learn more, you can take EC 552 in fourth year about computer architecture. So how do you design systems like this? What are some of the principles? And it's a deep topic, so you can study it in graduate school too. Okay, so far you've been writing single-threaded applications, at least in your work at U of T. So you've been using one core, and it's had all the memory. You didn't have to worry about anybody else touching memory because you were the only thread running. If you didn't touch memory, nobody else touched it. Once you have multiple threads, so now we've got, say, two threads running on two cores, and they're working together in one program to get something done. So that means they're sharing memory. And you need to worry about that. So you need to worry about what's happening with this memory that more than one thread could be modifying. Okay, so how are we going to parallelize? So there are a few different ways you can parallelize programs, like different libraries. The one that we recommend you use is OpenMP. So this is a little for loop that just takes three vectors. So A and B are inputs, and they have 100 elements in them. And we're just going to add A and B for every element and compute an output element C. So we're just doing a vector addition of 100 element vectors. So when you write that normally, a single thread would go through and execute this loop 100 times, and each iteration it would compute a different C. We can make this use more than one core with one line of code. So this is an OpenMP pragma. So a pragma, when you put hashtag pragma, that's an instruction to the compiler. If the compiler doesn't understand the pragma, then it ignores it, so it doesn't break your code. So if you ran this code in a compiler that doesn't know anything about OpenMP, then the for loop will just execute normally. It'll execute on one thread. It won't be any faster, but it'll work. If you run this, build this code in a compiler that does understand OpenMP, and G++, the compiler we use, does understand OpenMP, then it interprets this pragma as an instruction. It says pragma OpenMP parallel for. Parallel for is one of the OpenMP commands. It says the for loop that comes right after this line, you should run in parallel using multiple threads. Okay, so what happens? The compiler generates code to start up multiple threads, and on the UG machines, there are 4 cores, so it's going to start 4 threads, okay? And it's going to divide the work across those 4 threads. So you see the first thread takes entries 0 to 24, and it's going to compute the C values for those. Second thread takes entries 25 to 49, it's going to compute the C values for those, and so on. So each of these 4 threads only gets 1/4 of the work, but together they complete everything. At the end of this for loop, so right there, OpenMP also inserts code and inserts instructions in your program so that they will wait. Okay, so there's basically what's called a thread join. All four of these threads have to complete their work, and after they've completed their work, one thread will keep going, and that's your main thread, and execute the rest of the program. But basically, none of the threads will go past this point right after the end of the for loop until they're all done, which is what you want. So basically, when you ran this code serially in one thread, this for loop would be completely done before whatever next instruction was executed. When OpenMP divides it across four threads, it makes sure the same thing happens. Maybe these threads don't run at exactly the same speed. Doesn't matter. They will all wait until all of them are done, and then three of them will be destroyed, and the fourth one will keep going. Let's see. And Truman is asking, does OpenMP guarantee to spawn threads with the best scheduling possible? So this is a good question. So basically, what I've shown here is that each one of these threads gets 1/4 of the loop iterations. And maybe in this simple program, that's probably the right thing to do. In more complicated loops, maybe there's different amounts of work for each loop iteration. So maybe OpenMP could distribute the work across the threads in a more clever way. See if one is falling behind and take work away from it and give it to one of the other threads and so on. So Truman, it doesn't guarantee that it spawns threads with the best scheduling possible, because I don't believe that's actually a solvable problem. Like, you can't prove your schedule is the best. It does spend a fair amount of work. OpenMP has been worked on quite a lot to try to do a good schedule, like give the right amount of work to each thread, and use techniques like thread pools and so on. I haven't looked at what is the latest and greatest scheduling technique that OpenMP does, and it's probably changing all the time. So I'd say it does a good job of dividing work across the threads, but no program can say it does the best job. Hopefully that answers your question. And I think you could go read up on it to see. Yeah, so Truman's saying if one thread takes 8 seconds to finish and another takes 10 seconds, then that would be a bottleneck. What I'm showing here is a pretty simple scheduling technique where every thread got 1/4 of the work. OpenMP, you'd have to go look this up, and I have to look it up afterwards, but I believe OpenMP will actually do a smarter job of scheduling than this if one thread's falling behind. There are techniques to basically reallocate work if one of them is behind, or basically parcel out the work a little bit at a time. And OpenMP is pretty good at that, but I'd have to go look it up to see what's the latest thing it's doing. Okay. So good question. And I guess my answer is it's been worked on a lot. It does a pretty good job, but nobody can say it's perfect. And I can't say what all the details of how it allocates work is right now. I think it does work stealing, which is what you're talking about. But I haven't gone and looked it up recently. Okay, so let me show you a quick demonstration of this. And Abbott, if you know the answer, feel free to jump in. So. Okay, bring up, let's see. Okay, so I'm going to show you a really simple program that is, well, let me show you this first. Okay, so I'm going to type lscpu. Whoops, lscpu, all one word, tells me information about the computers that I'm on. So this is the UG machine. It basically says that it has, well, it says that it's 8 CPUs or 8 cores, but only 4 of them are online and the other 4 are offline. So this is really a 4-core machine. Why does it report it this way? These machines actually have 4 physical cores. That's what they really have. They have a technology in them that Intel calls hyperthreading, where they can run each core can run 2 threads at a time and get some additional throughput improvement. However, there was a security flaw found in that a few years ago, so it's off on these machines by default. So basically we have 4 cores, and that's why it tells you 4 of them are disabled. But the other 4 aren't really as good cores anyway. I have here a simple OpenMP program. This is very similar to the program. Let me get rid of this a bit. Okay, 1, 2, 3. Okay. This is a program that does some vector math as well. So it's similar to the simple vector addition, but a little bit more complicated. So what am I doing here? I've got a vector with 10,000 elements in it. And actually, I've got 3 of them, A, B, and C. So I create 3 vectors with 10,000 elements each. That's veclen. I go through and I basically, A and B are my inputs. I set each entry to some value using just some code. I don't really care what the values are. I'm just initializing them. I ask what the time is right now from chrono. And now I have a parallel for. So this pragma openmp parallel for says the next for loop should be run with multiple threads. And that for loop just goes through the whole vector, so from 0 to vector length, and it computes the output vector C. To do a little more work, slow the CPU down a bit, I do more than just add A and B. I do some multiplications, divisions, and modulus, but it's just computing every C entry from an A and B entry. I'm also going to print out how many threads we're using. So I can ask openmp get num threads. That'll tell me how many threads are being used to work on this for loop. And then after the for loop, I get the time, print out that time, and here I'll print out the number of threads used. Okay, so let's save that. I'm going to build this. Always should build with release if I'm testing time, which I'm doing. Okay, so let's run that. Okay, so it says that we used 4 threads. So that's good. That matches what I'd expect because it says we've got 4 CPUs online. So OpenMP figured out the number of CPUs and used the right number of threads. So that's good. And the time is really fast because I'm only working with vectors with 10,000 elements. So for a CPU, this is not that much work. So it took 7.8, 78 microseconds. So 78 microseconds is a number to remember. Now maybe this is slowing me down. So let's comment this out. I'm asking how many threads are there all the time. So I should probably just comment that out. So let's turn that off. Just in case it's slowing me down. I basically just needed that I wanted to confirm that everything was working well. I was getting multiple threads. Okay, so let's rebuild this. All right, and it looks like that wasn't slowing me down much, but I feel happier to have it off. Okay, so now it's 80 microseconds. Okay, so I want to see what did I gain by doing parallelism. So I'm going to turn off parallelism now. So I just comment out that parallel for line. Now this will run serially. It'll run in the normal way. Okay, so recompile it using the up arrows to select old commands. Okay, and that took 35 microseconds. Okay, so it took 80 microseconds here with parallelism on, and now it took 35, which means it's actually more than twice as fast in serial mode than it was in parallel mode. And I know parallel was using 4 threads because I had it printed out. So what's going on? Why do you think this happened? Yeah, and Mark is exactly right. So the startup is slow. Creating a thread takes a reasonable amount of work. So we created 3 additional threads, and then there wasn't that much for them to do. So our startup was slow enough that we really shouldn't do this. So let's go back. Well, let's increase the size of the vectors. So that's 10,000. Let's add 1, 2, 3, 4 zeros. Okay, so now I've got 100 million. So my vectors are much bigger. I'm going to rebuild this. This is still the serial code. So I'm going to run it again. Okay, so now the time is 0.34 seconds. Okay, that's the serial code. And let's turn parallelism back on. So I just have to uncomment this. Parallel for line. Let's rebuild. Let's run this again. Okay, now it's 0.09. So that's almost 4 times faster. Okay, if it was 0.085, this would have been 4 times faster. It's actually 0.09. So pretty close to 4 times faster. The difference is we're doing a lot more work. So we're starting up 3 additional threads. That still takes some time, but I'm doing, instead of a vector of length 10,000 where I'm doing some work on it, I've got a vector of length 100 million. So now I get some much more utility out of those additional threads. Let's see. What happens if you call parallel for on a nested for? Does it only do the outer loop? Yeah, I believe if you do parallel for on a nested for, it only does the outer loop. If you call it, what happens if you call it on each loop of a nested loop? That's a good question. I believe it does just increase the parallelism on, it'll just do nested parallelism. So you get more threads running. Um, that would generally only be a useful thing if you think your loops have a small enough iteration count that you would want to put parallel for on both the outer and the inner. If your outer loop had 100 iterations and you have 4 cores, then putting a parallel for on the outer loop is going to be plenty. If your outer loop goes through 3 iterations, your inner loop goes through 3, and you've got a 16-core machine, then putting a parallel for on both could be useful to try to expose more parallelism. Does that make sense? So, I mean, as we just saw, there is an overhead to starting threads. So you don't want to just throw parallel for everywhere. You want to basically put enough parallel for in that you can keep all your cores busy, and there's really no gain, and in fact, some danger to just throwing parallel for on, in lots of other places, trying to create many, many threads. Now, OpenMP does have a scheduler in it, so it tries to be smart rather than just doing, but you're now getting into, if I do nested parallel fors, exactly what is the scheduler? And you'd have to go look that up. So yeah, to Truman's point, would that become slower due to diminishing returns? Yeah, I guess what I'm saying is I would only do it if I can't get enough parallelism. I can't use all my cores by just parallelizing the outer loop. In that case, I could put parallel for on both, but if I already had plenty of parallelism, then I'd probably be better not to put parallel for on both. Okay, so does that make sense to everybody? Okay, so let me switch back to the slides. Oops, let's shrink this down. Okay, so we kind of just showed this, that speed up problem size matters. So I didn't show you all these cases. I showed you 10,000 and 100 million. But basically, this chart is showing that serial is much faster than parallel if you have really short vectors in the sample code I showed you. So speed up is the time that serial takes divided by the time parallel takes. So greater than 1 is good. If for really short vectors, using this parallel for actually slows things down a lot. Speed up's less than 1. We have to have vectors of about 1,000,000 before we start getting speed ups above 1 from parallelizing. And 100 million was pretty good. Okay, so in this chart it says 3.4. We actually did a little better than that. We were probably more about 3.7. So for that amount of work, we've really covered the startup, and it was fine. Okay, so let me animate through that. Okay, so don't parallelize small amounts of work. Only go for big amounts of work. So in milestone 4, pathfinding is a fair amount of work. So we can parallelize that. Let's talk first about algorithm. And we mentioned that at the start of this tutorial and also in lecture. We could use our A-star algorithm for milestone 4 or milestone 3 and just put a double loop around it. And if we have 24 interesting intersections, that takes about 32 seconds. If we improve the algorithm, so we use multi-target Dijkstra, we change the complexity from k squared n log n to k n log n, we get a nice speed up. Time drops to a little less than 6 seconds, 5.5x speed up. And that speed up will increase as we go to bigger problems. So this was really good. We can take, let me change my color here. We can take that that double loop over an A star algorithm, and we can make that parallel. So we use parallel for on that, and we'll get a speed up. So the time would drop to 9 seconds. We get a 3.5x speed up. But we can also parallelize our smarter algorithm, the multi-target Dijkstra, and that gives us our best overall answer. Okay, so a total speed up versus a serial naive algorithm of about 17.5x. So why am I showing you all this? Well, if you basically went off and parallelized the inferior algorithm, you would still not be happy. It wouldn't be as good as a serial version of a good algorithm, and it certainly is not nearly as good as a parallel version of a good algorithm. So this is a general principle. Before you start trying to parallelize things, you should work on your algorithms. Make sure you've got good algorithms before moving to parallelism. You can generally get larger gains from algorithms, and they're usually easier to debug. Parallel code can be hard to debug. Okay, so let me move on to demonstrating what does this look like for pathfinding in milestone 4. Okay, so I'm going to show you little bits of our reference solution and walk through some gotchas. Okay, so let me bring this up. Okay, so let's look at. So this is okay. So our milestone. This is the milestone 4 reference solution that we have, and this is going to be way more code than you can understand, which is good because we don't want you implementing the same thing. But the first thing our milestone 4 reference solution does for the better reference solutions is it figures out all of the travel times between the interesting intersections. So it does that kind of pre-compute a matrix of travel times that we showed you in lecture. Okay, how do we do that? Well, we do the smarter algorithm. So we're going to loop over all of the possible, we loop once over the interesting intersections. So for every possible start intersection that we might care about, we're going to call a multi-destination Dijkstra's algorithm, multi-destination Dijkstra algorithm, okay? To find all the paths that started at that intersection. And we can do it in parallel. So that's what this OpenMP parallel 4 is doing. Okay, so this loop over all of the starting intersections can be parallelized with this one line of code. Let's see, Truman is asking, this is a different year's code because you can see right and left turn penalties. Yeah, we changed the problem some every year just to mix things up. Our reference solution often has underlying features that we don't expose to you. So you are only getting a turn penalty. This solution can handle different left and right turn penalties, but you will not have to. Okay. Let's see. So I have a question from Maz of, could you explain what multipath Dijkstra does again? So multipath Dijkstra is it. Let's see. Let's see if I can basically bring up something I can draw on quickly. Let me draw on this. So multipath Dijkstra is basically for a certain source intersection, it just runs Dijkstra's algorithm, which is basically keep putting nodes that you can reach in a wavefront that are expanding outwards. You're finding better and better paths. And there are a whole bunch of places that you might want to find. All the other intersections that are interesting for that you have deliveries or drop-offs at. Multi-destination Dijkstra just means you don't stop when you hit one of those. You just keep going. You either keep going until you hit all of them or until you've just gone through the whole graph. It'll be pretty close to the same answer for both. And then once you've done that, you actually know the shortest path from this source to every one of these dests. So you know the shortest path to destination 1, to 2, to 3, to 4, and to 5. And that's basically just the way Dijkstra's algorithm works. It doesn't really just find the shortest path to one node. It actually finds the shortest path to every node if you just let it keep going till it searches the whole graph. Given that, it's actually a really nice solution to filling in that matrix because one call of multi-destination Dijkstra can basically fill in an entire row of that matrix, whereas one call to A star would only fill in one entry. It would go from source to maybe one dest. Okay, so that's what A star would find. Multi-destination Dijkstra would find all of these in one call. Multi-destination Dijkstra maybe takes 4 times longer than a single A star call or 3 times longer. but because I can call it k times fewer, overall it's a much better algorithm for this problem. Okay? Does that answer your question, Mas? Okay, so let's go back to, that's great. Let's go back to the code. All right, so again, you don't need to understand the details of this, but you basically this is our start intersection. So we pass in an ID of the intersection we're starting from and some other data structures you don't care much about. And it's going to go find all the interesting paths starting at that intersection. And we can run it in parallel. Let's start off, let's turn this off. Let's turn off the parallel and just see what happens. Okay, so, and the nice thing about OpenMP is I just turned off parallelism with one line of code. I commented out one thing, so that was kind of nice. Let's see. Okay, so I'm going to build this again. And the default is release, so I'm going to get the release build. And I'm not going to run all of the unit tests, I'm just going to run one of them. So I'm going to run Toronto Easy, which has about 25 deliveries to make, so it's about the same size as what we've been talking about in the slides. Okay, so that's been built. Yeah, and if you don't know how to do this, you can just use the up arrow keys and down arrow keys to go through your old commands. It's very helpful. Okay, so I'm going to run EC297 exercise, milestone 4, but I only want to run one tester, the public easy Toronto test case. Okay, so I'm running that. It's going to start by loading the map. I don't really care about that. It's going to take a few seconds. And then it's going to start our traveling courier algorithm. Okay, so the map is loaded. Now it started the traveling courier algorithm. We've got 25 deliveries to make. Pathfinding took 5.1 seconds, which is not too bad. But it's, some of the problems are going to be about 10 times this big. So that is, maybe not 10 times. Some of the problems are going to be like 5 times this big. So this could take a large part of my 50-second time budget. If I ran a problem 5 times this large, this would be 25 or 30 seconds. I lost a lot of my time to pathfinding. So if I want to do better, what I'm going to do is now I'm going to turn on parallelism. Okay, so they basically just turned on that OMP parallel 4 again. Whoops, didn't want that. Whoops, I'm hitting the wrong hotkeys today. Okay, so let's see if I can save this. All right, let's get rid of that. Okay, so let's rebuild that again. And run it again. Okay, so I rebuilt it. The only thing I changed is I turned on parallelism. I made that a parallel 4, which means I have multiple multi-destination path searches going on at the same time. I'll have 4 of them going on. Each of those 4 will be starting at a different start intersection. Okay, and my pathfinding time went from 5.1 seconds down to 1.44 seconds. So that's a speed of about 3x. So pretty good. I didn't quite get 4x, but it wasn't far off. And as I go to bigger problems, the speed up actually gets a little closer still to 4. So it's pretty worthwhile. And otherwise, everything works fine. Okay, so let me go here. And so I guess that shows you can get a benefit from making this algorithm parallel. I'm going to go take a let's look at what goes on in this algorithm a little bit to see some of the things that can go wrong. Because this looks a little, let's go back here. Let's see if I can go back and, okay, so you're not going to be able to read all this code, but you don't have to. Okay, so this is our code to do multi-destination Dijkstra. And right now, this is good code, okay? Good parallel-friendly code. How is it parallel friendly? It uses local variables for the priority queue. Okay, so you see there's a priority queue here that we're creating. So that's where we're storing our wavefront. And it is a local variable that is created inside the routine that we're calling in the parallel for. That's good. Okay. Why is that good? Because OpenMP, basically every thread gets its own copy of the local variables. So, and that's actually what I'd want. I have 4 path searches going on at the same time. I'd actually like each of them to have their own priority queue because it's logical. And that's what I have right now because I actually declared the priority queue as a local variable in the function that is being called in the parallel for. Other key data structure that we needed for Dijkstra's algorithm was this nodes data structure. We called it all nodes in our reference solution. So this is basically the data structure that stores what is the best cost found to any node, what is the reaching edge found to that node, etc. So it's a vector over all of the nodes. And again, it's a local variable. So it's defined inside this function, and then we initialize it, and then we use it in our pathfinding algorithm. And you already saw that this works, right? We completed the test case that I showed you, and nothing went wrong, and we got a good speed up. Okay, let me show you. I've got a couple of defines here that look kind of funny, like bad parallel global to bad parallel global. So those look kind of funny, and they are funny defines because they're defines that allow me to rapidly break the program. Okay, so what I can do, if I uncomment this define, let's do this one first. Let's see, which one of these do I want to do first? Let's do this one first. Okay, so I'm going to uncomment define bad parallel global. What I just did is I have now declared that all nodes, my node vector that stores what's my best travel time, what's my reaching edge for every node, I made it a global variable. Okay, and if I go back to where I was, basically you'll see this is grayed out. So my local variable is gone, and I've switched it to a global variable with the same name. So let's build this. I've copied over the unit test that for Toronto Easy. So all the unit tests are in the public directory that you know about. So I've copied over that unit test so I can compile it and run the debugger on it. Okay, so I've chosen the unit test debug build, going to compile, and I'm going to run this. Okay, so I've actually done a bad thing in my program. I took a nice local variable, I made it a global variable. Normally that would be considered not the best style, but with parallel code it's worse. So because the global variable is shared by all threads. So I'm going to have 4 copies of my path search algorithm running, and they're all going to be using the same global variable to keep track of for every node what's the best time found to it, what's the reaching edge, and so on. Okay, so this compiled. I got a bunch of warnings because this is kind of a hacky thing to do. I basically just changed a variable from local to global, and I did it in an easy way. So I'm going to run this, and let's just see what happens. Yeah, and Truman's saying, won't this cause race conditions and therefore a lot of seg faults? So yeah, this is really bad. I basically have multiple threads that are going to be writing to the same global variable, and that without any control, they're all just basically using the same global variable, but they're doing different path searches and they're going to be updating it in different ways. It's chaos. It is complete madness. So it's not going to work well. Let's see what happened. So I ran it, and you see it actually crashed. It says double free or corruption. So that one change just broke my program, and I got a memory fault. Okay, that was just running it. Now I'm going to run it through the debugger. Okay, because I'm confused. What happened? I need to figure out what's going on. So I'll run it through the debugger to try to get a better answer. Let's see. Mark is saying, wouldn't it work out if they were all doing parts of the same path search? It's possible, though. You have to think about it really carefully. So basically, if you have shared variables, you have to very carefully think through when can different things update them? Can that ever cause me problems? it's okay for multiple things to read from the same variable. That's fine. But it is not okay for multiple things to write to the same variable or for one to be reading it and another writing it. Um, so yeah, you don't want to be doing that. Okay, so I'm running this again, but now through the debugger, and we'll see what happens. So hopefully this crashes and I can see what's going on. The other thing that can happen though is I mean it might hang. And parallel programs, when you have race conditions like this, are very hard to debug because every time you run it, the order in which the threads access memory can be a bit different, which means that their behavior can be different. You have a program that is just not behaving well. You saw when I ran it the first time it crashed. It looks like this time it's not going to crash. It actually looks like it's gotten into an infinite loop. So, and you might go, well, how could that happen? It's because I have multiple threads that are not synchronized. They're all working at different rates and they're all writing to the same shared global variable and making decisions on that shared global variable. So depending on exactly who got where when, the program can now behave in different ways. So this is hard to debug. You do not want to do it. And yeah, it looks like this is actually hung this time. So what I'm doing is I'm running it in the debugger. I can hit pause. So I can hit pause and see what's going on. And okay, so it's now paused. When you're debugging a multi-threaded program, one of the things you want to know about is I went window debugging, window debugging threads. Okay, so I can open up a threads window. It's down here now. And what does it show me? It shows that I've got 4 threads. So I can double click on each of these to make them the active thread and go look at where it is. So I clicked on this thread and now I look at its call stack. So click on call stack. There's a whole bunch of low level C++ standard library stuff and memory allocation stuff. I don't know what any of that is. So I want to go back in the call stack to a point where I get to some code I wrote. Okay, so where is it? It's basically this thread is trying to push something back in a path. All right, so trying to remember that. Let's look at the next thread. Where is it? Okay, a bunch of stuff that I don't know. I'll go down in the call stack to a place where it's my code. This one is trying to look something up from that all nodes data structure. So remember, all nodes is the data structure that we made global and we're sharing in a chaotic way. So we're trying to access it in this thread, trying to read from it. Okay, let's see what else is going on in the other two. Okay, let's look at the call stack of the third one. Third one is right here. It's trying to clear it. So it's trying to clear that all nodes global variable. And let's look at the fourth one. Look at its call stack. And it's trying to push something back into a path variable. So I don't 100% know, why is like what's going on here. I do notice a couple of the variables, a couple of the threads are looking at that all nodes global variable. That might not be enough for me to figure out what's going on. I can try hitting continue. So let's see if this crashes. And it looks like it's not. So it basically is something, it's messed up that global variable, and it looks like it's making it go into an infinite loop. And that can be quite hard to track down. I went and looked at all the threads. 2 of them are accessing that, but there's not really anything that would make it obvious, tell me that that's the problem. Okay? And let's see, if I stop that again, let's see where they are. Okay. So yeah, the program looks hung, basically. It's just stuck there. But exactly why I'm going to have to run this multiple times, really do some investigation. It's a pretty tough debugging exercise. Okay, so let me stop that. One thing I can do, though, is if I suspect that parallelism might be one of my problems, what I should do is I should go and turn off parallelism. So let's turn off parallelism, and let's see if that fixes it. Okay, so I'm going to save this, I'm going to rebuild, and I'm going to run it again. Okay, so same exact code, still have a global variable for my node data storage, but I've turned off parallelism. Okay, we're into our traveling courier problem, and this is going to take a little while to do the path searches because we're doing it serially and we're in debug mode. So this might take 15 or 17 seconds. And it did, but it worked. So it did. It was slower. It took 15 seconds, but it passed. Okay, we finished. We finished the test. It worked. Okay, so that tells me something. I've got a problem with parallelism. Maybe hard to debug, but at least I know it's that. Let me go back to. Let me turn parallelism back on again, and let me go to. Let me go to my bad parallel global. Okay, so I'm gonna fix up that node data structure again. So I'll turn off my bad parallel global, and that makes it a local variable again, which is much better. And now I'm gonna basically make my priority queue a global variable. Also a bad thing to do. You think of I've got 4 path searches going on from different starting locations, and they're all sharing the same priority queue. I mean, this is kind of madness, right? It's like you're doing an exam with somebody from chemistry, somebody from English, somebody from history, and you're all madly writing on the same exam paper over top of each other's writing. Like it's going to be chaos. So I don't expect this is going to work well. Um, but the idea is I might not have known not to do this. So let's see what happens if I run that. So if I run this, let's just run it through the debugger and let's see what happens. Okay, so it's going through load map. Okay, it started a traveling courier. Okay, and this one actually crashed pretty quickly. So what did we get? Um, we got an abort signal. We got an invalid size from malloc. So we got a memory fault in this one. I'll hit discard and pause so I can look at it. Again, I have this threads window. The thread that is bolded is the active thread. That's the one that the debugger is showing me. It can only show me one thread at a time. And the one that it's showing me will be the one that crashed. Okay, so the debugger tries to show you the one that it thinks is most interesting. There's a whole bunch of low-level C++ code because there was an error. It's showing you all the error handling code. So I need to get back to something I understand. And it's here. Okay, so it crashed on resizing this all nodes routine. Okay, let's see what else was going on. And let's look at the second thread. Second thread was checking if the priority queue was empty. Okay. Um, third thread was trying to take something off the top of the priority queue. And the fourth thread, let's see. And the fourth thread was also checking if the priority queue was empty. So again, parallel bugs can be hard to figure out, but 3 of my 4 threads were actually accessing the priority queue. Now, the one that actually crashed in this particular run wasn't, so that's going to be confusing, but probably what actually happened is we've already corrupted memory, and essentially the 4th thread where it crashed was just more of a symptom of that. That's where the memory of the program in malloc has been corrupted, and that was the unlucky thread. The fact that 3 of the 4 threads are in the priority queue is actually probably more relevant. I'm going to run this again. Actually, stop. Let's stop the debugging. I'm going to run it again. And we'll see if we get the same error, because this is where you get into non-determinism. That in a parallel program where we're accessing memory in an undisciplined way like this, a shared global variable that we're reading and writing to, we may not get the same error every time. So again, makes it challenging to debug. Okay, so it's running. Traveling courier has started. And this time it hasn't crashed for a while. So it is actually behaving differently. With these race conditions, you don't get the same thing happening every single time. If that happens to you, do exactly what we just did a minute ago. Comment out the parallelism. If it goes away, that is a strong, strong indication that you have a race condition in your parallel code. So this looks like it's gone into a different problem. This looks like it's hung because it's not crashing, but it doesn't seem to be giving me paths. So I can hit pause and I can see where am I. So I can go to threads. That thread is in, it's checking if the queue is empty, priority queue is empty. Let's look at the second one. Second thread is checking if the priority queue is empty. Third thread is trying to take something off the top of the priority queue. And the fourth thread is also trying to pop something off the priority queue. Okay, so this again is all pointing to race conditions. Now in this case, the program hung and all four of my threads are trying to access the priority queue. So a strong indication I should look carefully at that priority queue. And in fact, it is broken because I made it a global variable. So I'm going to stop debugging and let's go back to the slides quickly. Yeah, so Trim is asking, is this now a deadlock? It looks like a deadlock. It looks like they've actually gotten into a state where basically you've got two things trying to take something out of the priority queue or check if it's empty. And so you can get into situations where one of them has updated part of the priority queue variables. Each of them has done some update to some of the priority queue variables where that has broken the priority queue. It's now gone into some kind of infinite loop or deadlock. I don't know exactly what's happened. It's really hard to say, but it's broken. Okay, so let me just quickly reiterate what we just did. The good code is actually, well, the bad code is on the left. We had a couple of global variables. One of them was the priority queue. So we have a shared global, and we use it inside of parallel code, which means everybody's sharing the same priority queue. And that's kind of chaos because they're all writing to it in undisciplined ways and reading when somebody else might have written to it. The fix is inside of our parallel for. So there's this parallel for loop. It calls this function find paths. And the fix is that find paths should have made the priority queue a local variable. If it's a local variable inside this loop or in any of the functions that it calls, then every thread gets its own copy. They cannot conflict. It works much, much better. Okay, so how do we debug parallel programs? So a standard thing you do is you turn off parallelism. If problem goes away, then you've immediately figured out it's probably a race condition then. Your serial code works. Something goes wrong with parallelism. You probably got multiple threads writing to, or some writing to and some reading a shared variable. So these are hard to debug, but at least you've figured out it is a race condition by turning off parallelism. You can run in the debugger. I showed you the threads window. So you open that up to see what's going on in different threads. You can look at their call stack. You can see when they crash, are they accessing some shared variable? Because that helps you figure out, well, that shared variable probably then is probably part of your race condition. Fixing race conditions, best way to do it is what's called privatizing the variables. So every thread gets its own copy, which means make it a local variable. Another way you can do this, which is not as good, but sometimes you have to do it. In milestone 4, you shouldn't have to do this. You can use OMP critical. OMP critical is OpenMP critical section. That means only one thread can go through the code that you write right after OpenMP critical. So the threads will negotiate through something called a lock variable or a mutual exclusion variable who gets to execute that code, and only one of them will execute it at a time. This is not as good a solution because you have to write some more code. You have to write this OMP critical, and it usually costs performance. The way it works is you're saying only one thread can go through the following block of code at a time, which avoids race conditions, but cost performance. In the particular, and in this particular case of what I was showing you, that couldn't fix our problem. Like we fundamentally needed 4 priority queues or a priority queue per thread. Even if we basically put the priority queue in a critical section, meaning only one thread could access it at a time, it's still chaos. We need each of the four running Dijkstra searches to have its own priority queue. It just does not make sense for them to share it. So in the case I showed you, privatizing the variable is the only logical thing to do. Another limit to parallelization kind of goes back to the first thing we looked at, where we had the vector update. It's called Andos Law. Basically, if some of your program is fundamentally serial and some is parallel, the serial code will limit your maximum speed up. So let's say half your code is serial, but half you know how to turn into multi-threaded code. That's this blue line. Even with an infinite number of CPUs, you'll only get 2x speed up. If 95% of your code could be parallelized, could be multi-threaded, and only 5% of your runtime came from serial code, then with an infinite number of CPUs, you could get to 20x. So, you'd be a lot more interested in putting the effort in to speed up that program than the effort to speed up this program. Okay, so what are the takeaways? Improve your algorithm first. Bigger gains, usually easier. OpenMP pragmas are a pretty succinct way to express parallelism. Avoid modifying shared state. So your parallel code should not be modifying state that other threads can see. It minimizes bugs. Privatize your variables or make them into local variables so every thread has a copy. You want to parallelize large chunks of work. Small chunks of work, first, it's not worth your effort. You have to put a price on your time. And secondly, there's a runtime overhead to start threads, so you're not going to get a speed up anyway. And it is hard. So writing parallel programs is fundamentally harder than writing serial ones. So you want to get a serial algorithm working first and only try to parallelize things that are going to give you a significant gain, because it's going to take some effort. And yeah, as always, for agile programming, get something working simple, quickly. All right, so get a simple algorithm going, return a legal solution. Then you can try computing exact paths, getting better algorithms, and if you get all that working well, you can try parallelizing in order to get even more CPU time. But do it in this order. Don't try parallelizing first. Get something working and working fairly well before you try that. You don't have to write any parallel code for M4. You can get quite good solutions without it. So this is really, if you want to challenge yourself, learn some about parallelism. And that's it for today. So I'll hang around if there are any questions, but I think we're a bit over time.